This is mathheals.com if you want to come here to find more links to math YouTube videos. And let's take a look at curve sketching, a summary. And let's look at our first problem. I got f of x is equal to 2x to the third plus 3x squared minus 36x plus 12. And it says sketch a graph of the function labeling intercepts, relative extrema, points of inflection, asymptotes. I'm basically going to go through and find everything on these just so we can see all the different pieces. Well, the first thing is the domain, where our graph exists, x value wise. Now, if you got a polynomial, your domain by default is negative infinity to positive infinity. Now, next thing we're going to find is X-Intercepts. For your X-Intercepts, you plug 0 into the other variable. So we'll plug 0 in for y. So you got 0 is equal to 2x to the third plus 3x squared minus 36x plus 12. This probably doesn't factor very nice. Actually, it doesn't look like it factors at all. So let's do it on the calculator. There is a by hand method for doing it, but it's not very nice. We go to y equals. Actually, I'm in a different mode from trig. So let me come down here, put it back to where it looks like your calculator. Okay, so we'll press y equals. Did I not set that? Enter. Okay, I did that time. Okay, one more time. Okay, we'll press y equals. Clear to clear out wherever's not line. And then we got 2x to the third plus 3x squared minus 36x plus 12. Have to have 0 on y2. This process doesn't work unless you have 0 on y2. So down arrow to y2 and put a 0 there. Okay, so we're going to do second trace. And we want to choose intersect. And my graph's kind of zoom funny, so let me just press zoom and choose Z standard 6. Okay, now let me do it. So do second trace, choose intersect. I'll press number 5 to choose it. And it comes up asking us for our first curve in the lower left-hand corner. We'll just press enter on it. Then it comes up asking us for second curve, so press enter on it. And for our guess, we input an x value close to our answer. So I'll put in -5. Our answer is where it crosses the x-axis. And then press enter. And we get, I'll take this 2 decimal places, -5.19. Well, looks like we've got 2 more x-intercepts. X-intercepts where it crosses the x-axis. So if I do second trace, choose intersect, enter on first curve, enter on second curve, and we put 1 in for the guess. And we get 0.35. And we got 1 more answer. So do second trace and choose intersect. Enter, and I'll put in 3. And we get 3.34. Okay. Let's find our y-intercept. For the y-intercept, you always plug 0 into the other variable, so plug 0 in for x. So come up here to original function, And put 0 in for x. So we've got 2 times 0 to the third plus 3 times 0 squared minus 36 times 0 plus 12. So we get y is equal to 12. Fourth thing is the vertical asymptote. Vertical asymptotes you only have if it's a rational, a single fraction. So there is none. Fifth thing is the horizontal asymptote. Again, you only have that if you have a fraction, so there's none. And the sixth thing is the slant asymptote, and yet again, there is none. Okay. Seventh thing we're going to find is increasing and decreasing intervals. Well, to find this, you have to find a second derivative, or first derivative. Okay, so take our power, put it out in front, lower our power by 1. So again, take our power, put it out in front, lower it by 1, plus 3 times 2x, take your power, put it out front, lower it by 1, and negative 36x becomes negative 36, and then my 12 drops away. So that gives us 6x squared plus 6x minus 36. Well, to find our critical values now, we're going to, let me double check my derivative there, 6x squared plus 6x minus 36. Okay. To find our increasing and decreasing, we're going to set this equal to 0 and find our critical values. So I got 6x squared plus 6x minus 36 equal to 0. Factor 6 out, and that gives us x squared plus x minus 6 equal to 0, which factors using the PSD method as x plus 3 times x minus 2. Zero factor property. You get 0 on one side, you factor the other side, you set each factor equal to 0. Now, it won't do any good to set 6 equal to 0 because there's no x there. So I'll set the x plus 3 equal to 0 and the x minus 2 equal to 0. And we get negative 3 and positive 2. Keep in mind our derivative is, well, we could use this one, or actually you can use the factored form. So I could use this right here if I want for the next step. Okay, so we want to build our table of intervals. Clear over here is negative infinity. Clear over here is positive infinity. We want to pick test cases. So we want to pick a value between negative infinity and negative 3, like negative 4. Pick something between negative 3 and 2, like 0. And something greater than 2, like 3. And we want to plug that into our first derivative. Now I could plug it in up here, but this is probably the easiest one to plug it into, because all we really care about is a sign. So plug into f prime. Now 6 is always positive, so I don't need it. So let's just plug it into x plus 3, and let's start putting it. X plus 3, x minus 2. Okay, so if I put negative 4 in here, we get negative 4 plus 3 and negative 4 minus 2. Negative 4 plus 3 is negative. Negative 4 and negative 2 is negative. Negative times a negative is positive. So this is positive, so which means it's increasing. Now if I put 0 in, I got 0 plus 3 and 0 minus 2. 0 plus 3 is positive. 0 minus 2 is negative. Positive times a negative is negative, which means this is decreasing. And if I put 3 in, then we're going to have 3 plus 3 and 3 minus 2. 3 plus 3 is positive. 3 minus 2 is positive. Positive times positive is positive. So it's increasing. The reason why we didn't have to worry about 6 is it was positive, and that doesn't affect anything then. Okay, so now we know we're increasing and decreasing, and I need to scroll up, but I need to write down, let me find a piece of paper. Okay, so from negative infinity to negative 3, negative 3 to 2, and 2 to infinity. Increasing, decreasing, increasing. Okay. I'm out of room there, so let me scroll up here and continue it. So, we're increasing from negative infinity to negative 3. Okay. And then we're decreasing from negative 3 to 2. And then we're increasing from 2 to infinity. And that was number 7. So the 8th thing we're going to find is relative extrema. Well, that's relative min, relative max, and that's where it changes from increasing, decreasing, and vice versa, assuming the point exists. So see how this is increasing here and then changes to decreasing? This is going to be a max here. See how this goes decreasing and changes to increasing? This is going to be a min. Let me jot those down on my piece of paper here. So I got max at x equals negative 3. And min at x equals 2. Okay. So we're going to have a relative max at x equals negative 3. And we'll have a relative min at x equals 2. Now we need to find out the y parts. We need to plug these into our f of x. Try that again. Relative min at x equals 2. I'll only do one of these, and then I'll show you the very quick way to do it. Okay, so when I say plug it in, I'm going to take that and we'll plug it into our f of x. So we got f of 2 is equal to 2 times 2 to the third plus 3 times 2 squared minus 36 times 2 plus 12. Well, that's 2, 4, 8 times 2 is 16. 2, 4, 12 minus 72 plus 12. Which gives us, that's 24, 30, 40, minus 32. So our relative min is at 2, negative 32. I mentioned that there's a quick way to do that. We could do the same thing for the x equals negative 3. Since we have this in our calculator, we put our function here. Then we'll go into table set. So I do second and then window. You only have to do this one time. See where down where it says independent? I want a down arrow to that line. And on my right arrow, I'll put my flashing cursor on the ask and press enter. So it should look like this now. Then we'll do a second mode, exit out. And then we'll go into table mode. So we'll do second graph. And you may or may not have numbers here. If you have numbers, you can delete them. And here we plugged in 2. So let me check my work. If I put 2 in, press enter, I get negative 32. So let me put in negative 3 inner. And we get 93. So we're going to have a relative max at negative 3, 93. Okay, ninth thing we're going to find is concavity. Well, I have to kind of locate my first derivative. Oh, here it is. So my first derivative was f prime is equal to 6x squared plus 6x minus 36. So to find our concavity, we have to find the second derivative. So I take the derivative of that, which would give us 12x plus 6. To find a critical value, set that equal to 0. So 12x plus 6 equal to 0. And solve for x. So it takes 6 over, becomes a negative 6. Divide both sides by 12. And we get x is equal to negative 1/2. Okay, so we want to build our table of intervals. Here's negative infinity over here. Here's positive infinity. We want to choose our test cases. Something between negative infinity and negative 1/2, like negative 2. Something between negative 1/2 and infinity, like 0. And we'll plug that into our second derivative. So plug into f double prime, which is 12x plus 6. So if I put negative 2 in there, I got 12 times negative 2 plus 6. 12 times negative 2 is negative 24 plus 6 is negative, which means it's concave down. If I put 0 in there, 12 times 0 plus 6 is positive, which means it's concave up. So for a concavity, it's concave down from negative infinity to negative 1/2. Then it's concave up from negative 1/2 to positive infinity. Okay, I'm going to grab a drink here. Okay, so what was that? That was the ninth thing. So 10th thing. Points of inflection. Well, points of inflection occur where your concavity changes, assuming that point exists in your original problem. And we said our domain was everything, so all points exist. So here my concavity changes, so I would have a POI right here. So we have POI at x equals negative 1/2. Now I need to plug that back into my original function and find out what that's equal to. But again, I can use my calculator, because I already have that on y1. So I'll put in negative 1/2 and press enter, and we get 30.5. So our POI is at negative 1/2 and 30.5. If you want to put that in the fraction form, calculator is very nice for that. Since it's a nice, I'm assuming it's nice. Let me go over to it and look at it. If you put your cursor on it, it'll show you if there's more decimal places. Doesn't look like there is. If I exit out, I do second mode. If I type in 30.5 math, enter. That'll tell you what your fraction is in case you're curious. So this one would be negative 1/2 and 61/2. Now, the 11th thing we would find is the graph. Now, I've made these numbers up, so, there's no way we're going to get any kind of precision out of this. Relative max of negative 3, 93. We'd have to go up through 93 units to find our max. And here the min is down negative 32. So I'm just going to sketch a graph from what I see on my calculator here. So if I go ahead and press graph, since I have that on my y equals, then that'd be my graph. In theory, if I hadn't made these numbers up and all these would be workable problems, you could take all these and then find out what your true graph looks like. So I don't know, it looks something like that. Crosses, I think, at 12. Comes down, not as much, goes like that, more or less. Now we could also use our leading coefficient test to tell what it's doing. Leading coefficient test isn't as important in these. It's more important maybe in college algebra. The reason why is because it tells us the increasing, decreasing. So we know what it's doing. So we don't need to use that table. Let me save that. And we'll look at the next problem. Okay. F of x is equal to x to the fourth plus 2x to the third minus 3x squared minus 4x. I'll kind of do it from side to side, I think, on this problem, so I don't have to write things down and scroll up and so forth. First thing we'll look at is the domain. Domain is so easy on polynomials, it's everything. So negative infinity to positive infinity. Next thing we'll find is the x-intercepts. To find the x-intercepts, you plug 0 into the other variable, so plug 0 in for y. So we got 0 is equal to x to the fourth plus 2x to the third minus 3x squared minus 4x. Now I'm going to use my calculator to find this. Doesn't look like it factors or anything like that. You can use the fundamental theorem of algebra to do it, but we got x to the fourth plus 2x to the third minus 3x squared minus 4x. Have to have 0 on y2. Then do second trace, choose intersect, and that's actually what our graph looks like, by the way, but we'll get to that eventually. Looks like it crosses the x-axis in 4 places. So let me do inner on first curve, inner on second curve, and we put in -3. So our first one, and I guess I might as well just take it to 1 decimal place. -2.6. The next one, I'm going to do second trace, choose intersect. Inner, let me put a -1. The guess. It is -1. Next one should be 0, but let me see. Second trace, choose intersect. I'm just pressing 5 to choose it. Inner on first curve, inner on second curve, I'll put in 0. We're inputting x values close to where we think our answer is. And one more. Do second trace, choose intersect. Inner on first curve, inner on second curve, and I'll put 3 in for the guess. And 1.6. And those will be our x-intercepts. That's our domain. Okay. Now for our y-intercept. You always plug 0 into the other variable, so plug 0 in for x. So we got 0 to the fourth plus 2 times 0 to the third minus 3 times 0 squared minus 4 times 0, which gives us y is equal to 0. Okay, vertical asymptotes, there is no, we need a single fraction for that, so there is none. Horizontal asymptotes, we need a single fraction, so there is none. Our slant asymptote, there is none. Again, you need fractions for those. Okay, our seventh thing, we need to find our derivative, so we can do the increasing and decreasing. So f prime is going to equal to 4x to the third plus 6x squared minus 6x minus 4. And we want to set that equal to 0. So we got 4x to the third plus 6x squared minus 6x minus 4 equal to 0. Let me grab a drink here. I don't think it factors. I can definitely divide out of 2, but that probably wouldn't help me a whole lot. So let me come here. Now, I got my function on y1. I'm going to leave it there. I'm going to go down to y2, where my 0 is. I'm going to put my first derivative there. So I got 4x to the third plus 6x squared minus 6x minus 4. And I'll put 0 on y3. Now notice how these equals have shading on them. If I go up to y1, and see how it's all graphed there together now? It's kind of a mess. If I go up to y1, I put my flashing cursor on equals, and I press enter one time. Then on right arrow, you'll see the shadings off of it. And all we have is our second derivative on the graph now. Again, that's how you can turn graphs on and off on your display. So I'm going to do a second trace, choose intersect. Intersect's a nice way to solve anything that's set equal to 0. Looks like -2, so let me do inner, -2. And it is -2. Next one looks like maybe -1/2 or something like that. Let me put 0 in for the guess. Second trace, choose intersect. Inner, and 0. -0.5. Well, that's -1/2. And our third one looks like 1. So we do second trace, choose intersect, inner 1. And it is. Now, we could have done the fundamental theorem of algebra to do this, but this is so much easier. So those are our critical values. So we got -2 is our smallest one. We got -1/2, and we got +1. And here's our intervals. Clear over here is -infinity. Clear over here is +infinity. We want to choose test cases. Choose a value between -infinity and -2, like -4. Something between -2 and -1/2, like -1. Something between -1/2 and 1, like 0. And something greater than 1, like 2. Now we want to plug these into our first derivative. Remember on our calculator, where would we put our first derivative? If I go back to the y equals, we put our first derivative on y2. So let me go do a second graph, go in table mode, and I'll delete the numbers I have there. You notice I have a y2 column. That's where our first derivative is. So I'm going to put in -4, and I get -140, which means this is decreasing. If I put in -1, enter, we get a +4, which means this is increasing. And if I put in 0 and press enter, I get negative, which means it's decreasing. And if I put in 2 and press enter, we get positive, which means it's increasing. Now again, all we care about is the signs there, not the actual values. Calculator is really nice for helping you to figure out increasing and decreasing for the test cases. You still have to do the calculus part, but then that takes the mind-numbing, plug this back in the original function part out. Okay, so this is decreasing from -infinity to -2, and then it's increasing from -2 to -1/2, and then it's decreasing from -1/2 to 1, and then it's increasing from 1 to infinity. Okay, that was that 7? Okay, step 8, Extrema. So relative Extrema. Well, we have mins and maxes where our increasing, decreasing changes, assuming the graph exists there. See how this is decreasing, changes to increasing, so this is a min. Here it's increasing, changes to decreasing, so this is a max. Here it's decreasing, changes to increasing, so this is a min. So we're going to have a relative min at -2 something. We'll have a relative max at -1/2 something, and we'll have a relative min at 1 something. Those are my x values across the top, my critical values. Okay, now we need to plug these back into our original function. Well, let me go back to y equals. Remember our original function we put on y1. So I want to turn this back on. So I'm going to do a left arrow and put my flashing cursor on equals and press enter one time. And then press the right arrow key. And I see y1 is back on. So let me go back to second graph, table mode. Delete those, kind of clean them out. And we got -2. Enter. Remember y1 is our original function. So that's relative min and -2, -4. And then relative max -1/2. So -1/2. And I can, if I want to see more decimal places, I can up arrow and right arrow, put my cursor on that, and it says 1.0625. And then the relative min, I'll down arrow here, left arrow, and we'll put a 1 here, and we get -4. Let's say I wanted to convert that 1.0625. It looks like it's doesn't go on forever, because if I up arrow that line, put my right arrow here, there's no more decimal places. So if I were to exit out to a second mode, 1.0625 math, enter, I get 17/16. So this one here could be written as -1/2. Try it again. -1/2 and 17/16. And that's our relative extrema. In terms of graphing, decimal actually works out better because we're in a world of 17/16 at. You know where 1.06 is roughly. Okay, so now we need to find our concavity, our 9th item. Well, I need to find my first derivative. I guess that's it there. 4x to the third 4x to the third plus 6x squared minus 6x minus 4 equal to 0. Oops. If we don't want it to equal 0. Okay, let's find our second derivative. That would give us 12x squared plus 12x minus 6. To find our critical values, we set that equal to 0. Now here I can factor a 6 out, and that gives us 2x squared plus 2x minus 1 equals 0. And I don't think that factors. Four x to the third plus 6x squared minus 6x minus 4, and then 12x squared plus 12x minus 6. Factor out of 6. No, don't think that factors. Okay, so I'm going to come here, and I'll press my y equals. Now, remember I have this on y1. I'm going to turn it off, so put my cursor on the equals, press enter one time. I'm going to come down. Y2 is where I had my first derivative, so I'll press enter on that, turn that off. And I'll go down to y3. In y3, I'll put my second derivative on there. So I got 12x squared plus 12x minus 6. And I want to put 0 on y4. There we go. Now we want to find out, we're wanting to solve this. And I'm not wanting to use the quadratic formula. I just want to find a decimal. So I do second trace, choose intersect. Crosses looks like a -1. So we do enter our first curve, enter our second curve, and we put a -1. -1.4. And then our next one looks like maybe a half. So second trace, choose intersect, enter, and we put 0 in. And that's x equals 0.4, taking them both to one decimal place. Now in terms of graphing, again, coming up with radical answers may be nice. It's exact answers, but it doesn't help us any in terms of graphing. And that's what we're looking at here, is the curve sketching. Even though we're not going to do a whole lot of that, we're showing all the different pieces. And I'm going to grab a drink here. Okay. Those are our critical values. So here's x equals -1.4. And here's x equals 0.4. Here's positive infinity, and here's negative infinity. We'll pick test cases. We'll pick a value between negative infinity and -1.4, like -3. Something between -1.4 and 0.4, like 0. And something greater than 0.4, like 1. And we will plug those into our second derivative. Now remember where our second derivative is. Second derivative is y3. So if I go to second, graph, table mode again, I'll press delete to clearing those out. Put in -3, enter. We get a positive 66. So it's positive, so it's concave up. If I put 0 in, press enter. It's negative, which means it's concave down. And if I put 1 in, it's positive, so it's concave up. So for a concavity, It's concave up from negative infinity to negative 1.4. It's concave down from negative 1.4 to 0.4. And then it's concave up from 0.4 to positive infinity. Now our POIs, the next thing we're going to find, I think was number 10. 10, yeah. Our POIs occur when the concavity changes, assuming that point exists. Now here it changes from concave up to concave down, so this is a POI. And this changes from concave down to concave up, so this is a POI. And I know it exists there because my domain, remember, was negative infinity to positive infinity. So we're going to have a POI at negative 1.4 something and 0.4 something. Now we want to plug those back into our original function. So let's come over to calculator, press y equals. Our original function was y1. So I'm going to press my left arrow key, press enter on equals, down arrow to y3, left arrow, turn off that one, up arrow to y2, that one's already turned off, isn't it? Okay. So we got our first one turned on, so do second graph to go in table mode. And I'm putting in negative 1.4. Which gives us negative 1.9. And I'm going to put in 0.4. Which gives us negative 1.9. That's interesting. I mean, it looks like there's symmetry with some of these, so that kind of makes sense. If we look at our original graph here, see how there's some symmetry there? Okay, now the last piece, actually come up with our graph. You know, I could just take with the TA3. This one I might be able to sketch some of it. Like here's our X-Intercepts, negative 2.6. Negative 2.6, maybe right there. Negative 1 and 0. Negative 1 and 0. And 1.6. Right there. So those are X-intercepts. Y-intercept is passes through the origin, so the Y-intercept is the same. Okay, so our relative extrema, min at negative 2, negative 4. Negative 2, negative 2, negative 4. So that's a min. And then a relative max at negative 1/2 and 1. 0.06, so negative 1/2. So negative 1/2 is about right there, and 1.06 maybe is right there. A little bit too far over. So that's a max. And then a min of 1, negative 4. Now POI is where the concavity changes. I'm not very good at doing POI anyway, but negative 1.4, negative 1.4, and negative 1.9. It's maybe right here where the POI is. 0.4 and negative 1.9. Maybe right there is also where my POI is. And then it starts out decreasing increasing, and so forth. So I could plot some additional points, but it looks like the graph's coming down, decreasing, reaches this low point, turns around, it's concave up, but here is where it kind of changes to where it's concave down. Goes up to there, passes through here, concavity changes a little bit there, I don't draw them very well. Goes up like that. And again, we use that to kind of sketch our graph. But a very nice way in your calculator here is you have to make sure your functions turned on and these other ones are turned off. But if I press graph, we get a much better picture. But sometimes the TI-3, TI-4 lies. So I mean, that's what this is about, is getting a true picture of what it looks like. And I won't always be able to graph all of these, because just when you make things up, they don't come out where you can graph them on a typical scale. Let me save this problem, and we'll look at the next one. Okay. Let me grab a drink here. Okay, so I want to do the same steps on this one. Okay, so we got f of x is equal to x, and then square root of x plus 2. Okay, our first thing is our domain. Now for your domain, if you have a radical with an even index, and that's what a square root is, you take what's underneath the radical, and you're going to set it greater than or equal to 0. Can't have any negative numbers inside of a radical with an even index. So we get x is greater than or equal to negative 2. So if I find any critical values, any mins and maxes, any POIs that are less than negative 2, I want to throw them out. Okay, our X-intercept. You always plug 0 into the other variable, so I plug 0 in for y. So we get 0 is equal to x, square root of x plus 2. Now whenever you have a 0 on one side and the other side factored, you set each factor equal to 0. So I'll set x equal to 0, and I'll set square root of x plus 2 equal to 0. Now x equals 0 is done, so it passes through the origin. This one, I can square both sides, and you get x plus 2 equal to 0. Take 2 over, and we get negative 2. Which, that's where our domain starts, so it looks like it touches the x-axis there also. Okay, our y-intercept. You always plug 0 into the other variable, so I'll plug 0 in for x. So I've got y is equal to 0 times square root of 0 plus 2, or y is equal to 0. Okay, number 4, 5, and 6. Want to find vertical asymptote, horizontal, and slant. Well, we need a single fraction, so there is none on these. Number 7. We need to find increasing and decreasing. Well, I want to rewrite this. This will be f of x is equal to x times x plus 2 to the 1/2. And we need to find our first derivative. This will be the product rule. This will be p, and this will be q. P prime will be 1. Q prime will be, and this is the chain rule. You got parentheses to a power, take a power, put it on front. What's inside the parentheses remains as is. Lower your power by 1, and then you multiply it times the derivative of what's inside the parentheses, which is the x plus 2. So that gives us 2 goes down here. X plus 2 to the negative 1/2. I want to move it downstairs. So x plus 2 to the positive 1/2. And the derivative of x plus 2 is 1, so it just drops away. So we want p prime q plus p q prime, our product rule. So for our first derivative, p prime is 1 times q, which is x plus 2 to the 1/2, plus p, which is x, times q prime, which was 1 over 2 x plus 2 to the 1/2. Now I want to write this in fraction form because I'm eventually going to get a single fraction. So we want x plus 2 to the 1/2 over 1 plus, now put the x up on top, x over 2 times x plus 2 to the 1/2. Want to get a common denominator, which would be this one here, since this one's 1. So we're going to rewrite each of them with 2 times x plus 2 to the 1/2. Now this one already has it, so we'll leave it alone. Here I multiplied the bottom part by 2 times x plus 2 to the 1/2, so I have to multiply the top part by it. So I got x plus 2 to the 1/2 times 2 x plus 2 to the 1/2. So I got a 2 up on top. X plus 2 to the 1/2 times x plus 2 to the 1/2. You add the exponents. 1/2 plus 1/2 gives us 2/2. And denominator stays as is. Okay. I probably should write some of this stuff down. I'm not going to be able to finish this in one page. I'm going to need new documents. So our domain was x is greater than or equal to -2. Our x-intercepts was 0 and -2. Our y-intercept was 0. Of course, I don't. Vertical asymptotes, horizontal, don't really need. Okay, so I need to merge these into a single fraction. So this will be 2 times x plus 2. 2 over 2 is 1 plus x over this. 2 times x is 2x. 2 times 2 is 4 plus x over. I should double check myself because I wrote so small there that x plus 2, that looks good. Not worrying about writing small now because I know I can't do this all on one page. So 2x plus x is 3x. That. We got our single fraction. And let me write that down because we'll need to take the derivative of that here in a minute. So that's our first derivative. So 3x plus 4, and then 2x plus 1 to the 1/2. X plus 1, x plus 2. Okay, to find our critical values, we're going to set top equal to 0 and bottom equal to 0. So we got 3x plus 4 equal to 0. Keep minus my first derivative. And we got 2 times x plus 2 to the 1/2 equal to 0. Well, this one, take the 4 over, becomes a -4. Divide both sides by 3, and we get -4/3. On this one, nice part about these critical values, if you got something inside of parentheses, number out in front, and a power, you drop the number, drop the power, and you just got x plus 2 equal to 0. So we get x equals -2. Okay, so then we want to set up our table. My smallest one, I guess, is the -2. And then -4/3 goes here. Clear over here is -infinity. Clear over here is positive infinity. I want to pick test cases. Something between -infinity and -2, like -3. Something between -2 and -4/3. -5/3. -5/3. The reason I say that is this is 6 over 3, so this is -6/3. That's -4/3, so -5/3. And something greater than -4/3, like 0. Now here's our first derivative. And let's go ahead and put that in our calculator. It makes these so much easier. Key to plugging in something that has a fraction into your calculator is you put parentheses around the top, parentheses around the bottom. unless it has just a single number or a single variable on top or bottom. Okay. Let me clear all these out. Now our let's go ahead and put this on y1. So we got x, second x squared for the square root, and then x plus 2. Closing parentheses. So that's our function. And then let's put our first derivative on y2. So we got beginning parentheses 3x plus 4, closing parentheses divided by beginning parentheses 2, beginning parentheses x plus 2, closing parentheses caret, and then since we have a fraction in the power, I had to put parentheses around it too. So you do beginning parentheses 1 divided by 2, closing parentheses, and then closing parentheses on the bottom part. Okay. And we don't got our second derivative yet, so let me just put a 0 here. And I'll get rid of the 0 on y4. We'll eventually put second derivative there, but now I want to shut off the first one, y1, the function, and this is our derivative. Okay, so now we want to do these test cases, and we're going to plug them into our first derivative. So those are our test cases, and we want to plug those into, again, our first derivative. Well, my first derivative is on y2. So let's go to second graph. You see I have y2 here. Let me press delete to clear those out from the previous problem. And I got negative 3, enter, error. Why do you think that's an error? Go back to your domain. Our domain was x is greater than or equal to negative 2. X is greater than or equal to negative 2 doesn't even exist here, does it? Now, if you don't remember the domain when you're doing these, it'll be obvious. You'll come up with something that's just really out there. It's just like, well, that doesn't make any sense. It does when you think about it. Now, negative 5/3. Negative 5 divided by 3, enter. We've got a negative value. So this is negative, which means it's decreasing. Then I put 0 in. And it's positive, which means it's increasing. Okay, so over here, let me write this. It's decreasing from negative 2 to negative 4/3, and then it's increasing from negative 4/3 to positive infinity. Let me write that down. Decreasing from negative 2 to negative 4/3. And it's increasing from negative 4/3 to positive infinity. Okay. I don't know what number we're on. 8, I think. 7. Okay. Yeah, we're on 8. 8 is our relative extrema. Excuse me. Well, assuming our graph exists there, where it changes from increasing, decreasing, or vice versa is our relative min, relative max. Well, this is decreasing and changes to increasing, so this is a min. Now, I know our graph exists there because our domain said that x is greater than or equal to negative 2, so it exists everywhere to the right of negative 2. Well, we got a relative min at negative 4/3. And we want to plug that into our original function. So I'm going to come back to here. I'll press my y equals. Our original function was on y1. So let's turn that on. I'll do a left arrow, press enter on equals. Right arrow. Down arrow, I'm going to shut the y2 off now. Okay. And I can shut off y3 if I wanted, but I'm going to do second graph, go in table mode. carefully to clear those out. And we want negative 4/3. And press enter. And we get negative, I'll take it to one decimal place, negative 1.1. Weird as it seems, decimals actually help us better in terms of sketching the graph. If I come up here, you can see there's more decimal places, and you see here there's a whole bunch. Okay, so let me jot that down on my piece of paper here, because I'm already starting a new page. And I got relative min at negative 1.3 and negative 1.1. I'm going to write down decimal, because that's what I'm going to use to graph it. And let me save this. Okay. Got my first derivative written down. I guess that's all I need. Okay, and we're continuing with this problem. So, we got our first derivative, which is 3x plus 4 over 2x plus 2 to the 1/2 power. Well, we're going to find a concavity now. I think that's 9. Well, we need to find our second derivative. So I use quotient rule. This will be p and this will be q. P prime, derivative of 3x plus 4 is 3. Q prime, the derivative of this, 2 remains out there. This is the chain rule. We've got parentheses to a power. Take your power, put it out in front. What's inside the parentheses remains as is. Lower your power by 1, so it'll be negative 1/2, times the derivative of what's inside the parentheses, which would just be 1. 2 times 1/2 cancels. So this gives us 1 over x plus 2 to the 1/2. So we got p prime q minus p q prime over q squared. So let's see what that gives us. P prime was 3 times q, which is 2 times x plus 2 to the 1/2, minus p, which is 3x plus 4, times q prime, which is 1 over x plus 2 to the 1/2, all over q squared. So we've got 2x plus 2 to the 1/2 squared. Double check all that. P prime times q minus p times q prime. Okay. So 3 times 2 is 6. X plus 2 to the 1/2 minus, I'll put the 3x plus 4 up on top there, x plus 2 to the 1/2, and this down here, square the 2, that gives us 4, and square this, and that gives us x plus 2 to the first power. You raise one exponent to another exponent, you multiply them. 1/2 times 2 is 1. Now we got a fraction instead of a fraction, so we're going to multiply everything by the x plus 2 to the 1/2. So I got x plus 2 to the 1/2 times 6 x plus 2 to the 1/2 minus 3x plus 4 over x plus 2 to the 1/2 times x plus 2 to the 1/2 all over 4 x plus 2 to the first times x plus 2 to the 1/2. Okay, well our first part there, the 6 remains. X plus 2 to the 1/2 times x plus 2 to the 1/2, you add the exponents. 1/2 plus 1/2 is 1. So this just gives us x plus 2 to the first power. Minus, these right here are going to cancel. And I have to leave parentheses around this, so this will be 3x plus 4 all over 4x plus 2 to the first power times x plus 2 to the 1/2. You add the exponents. So that gives us x plus 2 to the 3/2. So that gives us 6x plus 12 minus 3x minus 4. Negative out in front of your parentheses flips the sign of everything inside. So we've got 4 times x plus 2 to the 3/2. Well, 6x minus 3x gives us 3x. 12 minus 4 is 8 over this right here. And that's our second derivative. Okay, now I know I'm going to need it eventually on my my calculator. So again, I'm going to put it in there. Key is parentheses are on top, parentheses are on the bottom. So let's go put it on there. So press y equals, go down to y3, and I'll put a beginning parentheses 3x plus 8, closing parentheses divided by beginning parentheses 4, beginning parentheses x plus 2, closing parentheses, caret, parentheses around the exponent, 3 divided by 2, since it's more than a single number. Closing parentheses on exponent, closing parentheses on the denominator. There we go. Okay, let's find our critical values. So I'm going to set the top part equal to 0, and I'll set the bottom part equal to 0. Now here we got 3x equals negative 8, divide both sides by 3, and we got x is equal to negative 8/3. Now this one, remember if you have a number out in front and you have power, they just all drop away, and you got x plus 2 equal to 0. So we got x is equal to negative 2. See, our smallest one is this one. This one's x equals negative 2. Clear over here is positive infinity. Clear over here is negative infinity. Choose something between negative infinity and negative 8/3. That gives us, I don't know, negative 4. Something between negative 8/3 and negative 2. This is like negative 2 point something. How about negative 2.9? And over here, like 0. Okay, now think back to your domain. I've erased it, but your domain said x is greater than or equal to negative 2. What does that tell you about this interval and this interval? You don't need them, do you? You can plug them in. You might even get valid answers. Probably not. You probably get some kind of error. But let's plug in 0. I'm going to come to my calculator. See, I just put my second derivative on y3, so I want it turned on. I see y1 still turned on, so let me go turn it off. There we go. Now do second graph, go in table mode. Delete that. And then put 0 in. And it's positive, which means it's concave up. Okay. So, for a concavity, it's concave up from negative 2 to infinity. Now, POIs, number 10. POIs is when your concavity changes. Well, it doesn't change. It's concave up everywhere. So there is none. Now for our graph. Let me come up here if there's room. I don't see room. Let me save that. And let me grab a drink. Let's take the information I got and just kind of sketch it. Okay, what does that say? Domain x is greater than or equal to negative 2. That's where it starts. Here. And the x-intercepts is 0 and negative 2. So right here and right here. Our min is at negative 1.3, negative 1.1. Negative 1.3 and negative 1.1 is about right there, and that's our min. And then it's decreasing to begin with, and it changes to increasing. And concavity is concave up everywhere. And I could do points to get a little bit better picture of this, but looks like it's coming down here, reaching the min, and then it's going up like that. Now, how much of an angle is it at? I don't know. Let's actually graph it and see. So go back to here, press y equals. I'm going to turn off y3 because that's our second derivative. And I'm going to go up to y1 and turn that on. And let me press graph. Now the graph looks like it doesn't actually touch the x-axis. TI3, TI4 gives you the wrong graph sometimes. That's what this section is about, is finding the true picture. And that's it for that problem. So let's look at the next one. Take my glasses off. They're kind of hurting me with these headphones. Okay, so we got f of x is equal to 5x to the 2/3 minus x to the 5/3. And let's first go graph this. Put it on y1. Okay, so I got 5x caret, and I want to put parentheses around the power since it's more than a single number. So beginning parentheses, 2 divided by 3, closing parentheses, minus x caret, beginning parentheses, 5 divided by 3, closing parentheses. Okay. And let's see, first thing is domain. Now, normally these are radicals. When you got a fractional power like that, a rational exponent, that means a radical. But since our denominators are 3, that means our index will be 3. And for a radical with an odd index, your domain is everything. So domain is negative infinity, positive infinity. Well, X-intercept. We'll plug 0 into the other variable, so we'll plug 0 in for y. So we got 0 is equal to 5x to the 2/3 minus x to the 5/3. Now we can factor out an x to the 2/3. You always factor out the one with the smaller exponent. And what's that give us? 5, that's gone, minus x, and 5/3 minus 2/3 gives us 3/3, like that. So we got x to the 2/3, and then this becomes 5 minus x. Now I can set each one of those equal to 0. So I'll set the x to the 2/3 equal to 0, which gives us x equals 0 for x-intercept. And for this one, I got 5 minus x equals 0, or x is equal to 5. Let me write those down, because I think this is another one that's going to go off. So I got x equals 0, and x is equal to 5. Okay. Now our y-intercept. We always plug 0 into the other variable, so we'll plug 0 in for x. So we got y is equal to 5 times 0 to the 2/3 minus 0 to the 5/3, which gives us 0, which makes sense. If x equals 0, that's the origin. For our vertical asymptote, or horizontal asymptote, and our slant asymptote, oops, all of those are none. Okay. For increasing and decreasing, we need to find our first derivative. So take my power, I'll put it out in front. So I got 5 times 2/3 x, lower your power by 1. 2/3 minus 1 is negative 1/3. Minus, take your power, put it out in front, lower it by 1. 5/3 minus 1 is 2/3. Which gives us 10/3 x to the negative 1/3 minus 5/3 x to the 2/3. Okay. Now, it's interesting. There. I've shifted things to try to get my pen's not working. There. Okay. Put the x to the negative 1/3 downstairs. Becomes x to the positive 1/3 minus 5x to the 2/3 over 3. Now we want to get a common denominator, which would be 3x to the 1/3. So I'm going to rewrite each one of them with that new denominator. Now they both have 3, so I don't have to worry about that. Here I multiplied the bottom part. Actually, that's the same, isn't it? I didn't multiply by anything. Okay, never mind. Just kidding. Over here, I multiplied the bottom part by x to the 1/3, so I have to multiply the top part by x to the 1/3. Tablet going haywire there, kind of messed my mind up for a second. Okay. Now, 5x to the 2/3 times x to the 1/3. They're both x to a power, so you add the exponents. 2/3 plus 1/3 gives us 3/3 or 1. So that becomes 5x, and this is 3x to the 1/3. Which then tells us that our first derivative is going to be 10 minus 5x over 3x to the 1/3. Now let me write that down on a piece of paper here, because we'll need that later. 10 minus 5x over 3x to the 1/3. Okay. Actually, let me go ahead and put that in my calculator. Remember, the key is put parentheses around top, parentheses around the bottom. Like that. So, we'll go, okay, I already got that there. So on my y2, I'll put a beginning parentheses, 10 minus 5x. Closing parentheses, divided by, beginning parentheses, 3x caret. And since I have more than a single number in my exponent, I have to put parentheses around exponent also. So beginning parentheses, 1 divided by 3. Closing parentheses on exponent, closing parentheses on denominator. Okay, let's find our critical value. We'll set the top part equal to 0. So I got 10 minus 5x equal to 0. And we'll set the bottom part equal to 0. So 3x to 1/3 equals 0. Now here, take the negative 5x over, it becomes a positive 5x. Divide both sides by 5, and we get x equals 2. And here, drop the number in front, drop the power, and we just get x equals 0. So those are our critical values. Okay, so come down to here, and our smallest one, I guess, is 0, and then 2. Here's negative infinity, here's positive infinity. I'm going to choose a value between negative infinity and 0, like negative 1. Something between 0 and 2, like 1. Something between 2 and infinity, like 3. And we want to plug these into our first derivative. So plug into our f prime. So I put my f prime on y2. So let me go shut off y1. And go to second graph to go in table mode. just delete to clear that out. And I got -1, enter, and that gives us a negative. So this is decreasing. If I put 1 in, enter, we get a positive, so this is increasing. And if I put 3 in, press enter, it's negative, so it's decreasing. So for our increasing and decreasing, it's decreasing from -infinity to 0. Then it's increasing from 0 to 2. And then it's decreasing from 2 to infinity. Now, assuming our graph exists there, where it changes, that was, I don't know what that was, 7? Yeah. So our 8th, our relative extrema. Assuming our graph exists there, where it changes from increasing to decreasing or vice versa, there's mins and maxes. So this is decreasing, changes to increasing. So this is a min, and this is a max. So we're going to have a relative min at 0, something, and we'll have a relative max at 2, something. And let's go plug those into our original function. Let's think what I just said, original function. So I'll go back to y equals. I want to turn on my original function. Press enter on it. And go down to y2 and shut that off. Go to second graph for table mode. Clean those out. And we got 0 and 2. So 0, enter, 2, enter. So relative min at 0, 0, and relative max at 4.8. Like that. Let me write those down. So it's decreasing from -infinity to 0, increasing from 0 to 2, then it's decreasing from 2 to infinity, and our relative min is 0, 0, and our relative max is 2, 4.8. Okay, let's go back to our calculator. Right now our function is turned on, and that's turned off. And if I press graph, that's pretty bizarre looking. Relative min 0, 0. That looks reasonable. A relative max at 2, 4.8. Yeah, that looks reasonable. So, okay. Now we need to find our second derivative and find our concavity. So let me save that. There we go. Okay, so I don't even know what problem we're on. It's 4 continued, I guess. So our first derivative, 10 minus 5x over 3x, what am I think that says 1/3. Put my glasses back on. Yeah, I think it's 1/3. Okay, so we need to find our second derivative, so we find our concavity. And I think that's number 9, I believe. Yeah, this will be P, and this will be Q. So P prime, 10 goes away, this gives me a -5. Q prime, take your power, put it out in front, lower it by 1. So those going to cancel, and we got 1 over x to the 2/3. Okay, so we're going to have P prime Q minus P Q prime over Q squared. By the way, the reason why I looked at my graph there is one of the benefits of having a graphing calculator is once you find your min and max, look at it and see if it makes sense. That'll tell you if you made a math error. Okay, so for a second derivative, p prime was -5 times q, which is 3x to the 1/3, minus p, which is 10 minus 5x, times q prime, which is 1 over x to the 2/3, over q squared, which is 3x to the 1/3 squared. And let me double check those real quick. Looks good. Okay. Now we want to simplify this a little bit. So -15 x to the 1/3 minus 10 minus 5x over x to the 2/3 over square of the 3, that gives me 9, and square of the x to the 1/3, and that gives me x to the 2/3. Now we want to get rid of this fraction inside of the fraction, so we're going to multiply everything by x to the 2/3. So I got -15 x to the 1/3 times x to the 2/3 minus 10 minus 5x over x to the 2/3 times x to the 2/3. Then down here, multiply this by 2/3, or x to the 2/3. Okay, that's going to cancel with that. So let's see what we have. X to the 1/3 times x to the 2/3, you add the exponents. 1/3 plus 2/3 is 1. So that just gives us x. Minus, and we have to put parentheses around that because that negative is going to flip the sign of both of those. And down here, x to the 2/3 times x to the 2/3, you add the exponents. 2/3 plus 2/3 is 4/3. Which gives us -15x minus 10 plus 5x over 9x to the 4/3. Which gives us -15x plus 5x is -10x minus 10 over 9x to the 4/3. And that's our second derivative. Well, let's go plug that into y3 on our calculator. So put parentheses on top, parentheses around the bottom. We're going to plug them in. Okay, so I'll press y equals. I'm going to turn off the y1 while I'm here. Then go down to y3. And put parentheses, -10x minus 10. Close parentheses, divided by, beginning parentheses, 9x caret, and since we have more than a single number in our exponent, we have to put parentheses on it. So 4 divided by 3. Closing parentheses on exponent, closing parentheses on denominator. That's assuming I didn't screw up somewhere. Let me double check real quick. Okay. So I got that on y3 now. Well, to find our critical values, we set the top part equal to 0, bottom part equal to 0. So I got -10x minus 10 equal to 0, and 9x to the 4/3 equal to 0. So here, take the -10x to the right side, becomes a positive 10x. Divide both sides by 10, you get x equals -1. And this one give us x equals 0. So build our table of intervals. This is -infinity, this is positive infinity. Choose test cases. Something between -infinity and -1, like -3. Something between -1 and 0. -1/2. Something greater than 0, like 1. Now plug those into our second derivative. plug into our second derivative. Think what we're saying. We want the second derivative turned on, which it is. Now do second graph. Delete to clean those out. And we got -3, which is positive, which means this is concave up. -1/2. -1 divided by 2. It's negative, so it's concave down. And 1. And it's negative, which means it's concave down. That's weird. That's true, though. And the graph is just kind of weird, period, so I mean, that's not real surprising. Okay, so for a concavity, it's concave up from -infinity to -1. It's concave down from -1 to 0. And then it's concave down from 0 to positive infinity. Now our POI, number 10. POIs exist where the concavity changes, assuming the graph exists there. This is concave up, this is concave down, so this will be our POI. And our graph exists everywhere, so we're fine there. So we're going to have POI at -1 comma something. We want to plug that into our original function. So I'm going to come back here, go to y equals, turn my original function on, which is y1. And I'll turn off y3. Okay, now go to second graph for table. Delete to clean those out. And we'll plug in -1. And that gives us 6. And that'd be our POI. Now for your graph, we would just sketch our first one here. And that's already turned on, isn't it? So we press graph. Drag a little too much pop, otherwise I'd go through and graph this by hand. But that would be our graph there. So, actually, let me go ahead and sketch it here, real quick. Yeah, it's real smart drinking a lot of pop right where you're making one of your longest videos of the course. I'm not known for my intelligence. Ask my wife that. I think I can make it through the next one, though. Okay, let's look at our last problem. I think it's actually a little easier one, so that should work out good. Hopefully. F of x is definitely not a radical, so it's definitely easier in that regard. Equals x plus 4, x minus 1. Okay. Now your first one is your domain. If you got a fraction, you set your denominator equal to 0 and solve it. So we got x minus 1 equal to 0, which gives us x equals 1. Now this is the value we cannot have. If I put 1 in for x, I get 1 minus 1, which is 0. So our domain is x cannot equal to 1. Second thing is the x-intercept. We plug 0 in for the other variables, so plug 0 in for y. And try it again. 0 is equal to x plus 4 over x minus 1. Now when you're finding the x-intercept, not critical values, but when you're finding the x-intercept and you got a fraction equal to 0, you can just set top part equal to 0. So set the x plus 4 equal to 0. And then we get x equals -4. And that's our x-intercept. Now for our y-intercept, you always plug 0 into the other variable, so I'll plug 0 in for x. So I got 0 plus 4 over 0 minus 1. And we get y is equal to -4. It's kind of weird, it's the same. Our vertical asymptote. Our steps are to factor the top, factor the bottom, cancel if possible. Well, there's no factoring and there's no canceling here. So So we go straight to step 3, which says set your denominator equal to 0 and solve it. So x minus 1 equal to 0, and we get x equals 1. Now for a horizontal asymptote, our fifth thing. If your degree of the top is 1, degree of the bottom is 1, degrees are the same, then you create a fraction off of the number off the front of the x to the largest power. Well, here's x to the largest power, the number in front of it's a 1, and here's x to the largest power, the number in front of that is a 1. So our horizontal asymptote is y is equal to 1. Our slant asymptote. You only have a slant asymptote if your degree of the top is 1 larger than the bottom. So there's none here. Okay. Now our increasing and decreasing. Actually, let me go ahead and put that on y1 first. Now the key to putting these in your calculator is if you got a fraction, let me clear those out. Put parentheses around top, parentheses around the bottom. So when I plug this in to y1, parentheses around top, parentheses around the bottom. So I got beginning parentheses, x plus 4, close parentheses, divided by beginning parentheses, x minus 1. Like that. Okay, let's find our first derivative. So we got f of x is equal to x plus 4 over x minus 1. Quotient rule. This will be p and this will be q. P prime will be 1. Q prime will be 1. So we got p prime q minus p q prime over q squared. So p prime was 1 times q, which is x minus 1, minus p, which is x plus 4, times q prime, which is 1, over q squared, which was x minus 1 squared. So that gives us x minus 1. A negative flips the sign of both of those, so it becomes a negative x minus 4 over x minus 1 squared. Now x minus x drops away, negative 1, negative 4 is negative 5 over x minus 1 squared. And let me go ahead and put that on y2. Okay, so I'm going to have negative 5 divided by beginning parentheses x minus 1 close parentheses squared. Okay, find our critical values. Set top part equal to 0, but there's no x there, so don't need to do anything with it. We'll set the bottom part equal to 0. So we got x minus 1 squared equal to 0. Again, whenever you have 0 on the side, you got a power, you can just drop the power. So we got x minus 1 equal to 0, or x is equal to 1. Now remember what our domain is. We said domain x cannot equal to 1. So we're not going to have an extrema, but that doesn't mean that won't tell us something about the increasing and decreasing. So let's take a look at that. We want to pick test cases. I want to choose a value between negative infinity and 1, like 0. Some between 1 and infinity, like 2. And we want to plug those into our first derivative, which, remember, we put our first derivative on y2. So let me go shut off y1. And I'll go to my second graph. And clean out the old values. And I got 0, and I got 2. 0 gives us negative. 0 and 2 gives us negative. That's interesting. So it's decreasing, decreasing. So our intervals are decreasing from negative infinity to 1, and then decreasing from 1 to infinity. Okay. Our eighth item we're finding, the extrema. Well, it doesn't even change from increasing, decreasing, but even if it did, we can't have a relative min, relative max where the graph is undefined. And our concavity. What was our first derivative? Negative 5 over something. Okay, negative 5 over x minus 1 squared. Probably the easiest way on this one is not to use the quotient rule again, but to rewrite this as negative 5 times x minus 1 to the negative 2. And then we can just use the chain rule. So for our second derivative, take your power, put it out in front. Lower your power by 1, so it becomes negative 3. And then you multiply times the derivative, what's inside the parentheses, which is just 1. So that gives us 10 x minus 1 to the negative 3, which gives us 10 over x minus 1 to the positive 3. Take it back downstairs. Well, let's put that in our calculator. So go to y equals, put that on y3. So we've got 10 divided by, beginning parentheses, x minus 1 to the third, caret 3. There we go. Okay, find our critical values. No need to set top part equal to 0. There's no x to solve for. So set the bottom part equal to 0. And we get x minus 1 equal to 0. You can drop the power. And then you get x equals 1. Set up our intervals. I want to choose test case between negative infinity and 1, like 0. Something between 1 and infinity, like 2. Now we want to plug these into our second derivative. And remember where we put the second derivative? We put it on y3. So let's go shut off y2, just so it doesn't muddy the water. There we go. And now only have y3 turned on, which is our second derivative. So go to second graph, clean those out. And I said 0 and 2. So 0, inner, 2, inner. First one's negative, which means concave down. This one's positive, which means concave up. So for a concavity, this is concave down from negative infinity to 1. And then this is concave up from 1 to positive infinity. Now our POI is where the concavity changes. Well, it just changed here, didn't it? But at x equals 1, our graph does not exist. So there cannot be a point of inflection. So the answer is none there. Okay, now let me sketch this. We said that X-intercept is negative 4, Y-intercept is negative 4. So X-intercept, negative 4, and Y-intercept is negative 4. We said our vertical asymptote is 1, and horizontal asymptote is 1. Okay. Like that, and horizontal asymptote is 1. Now our it's decreasing. Okay. Now if I put it up here, this would be increasing. So I'll put it down here, so it's decreasing. Like that. And it's concave down, so that makes sense. And then over here, it's decreasing also, and it's concave up. So it'd look like this. So that'd be our graph. Who is it? Ryan. Actually, I'm just about done. If you give me about 1 minute. Got a phone call. So let me save that. There we go. And stop the recorders. 1 minute, 1 hour and 44 minutes. Wow. Okay. And stop this recorder for 5 problems. These aren't easy problems. Copy that. And I was using the calculator to do kind of the hard part.